In this video, I'm going to derive the following algorithm which fixes this parity case. I'm going to go ahead and play it real quick. Before I begin, I strongly recommend that you watch my derivation on the standard algorithm. So with the standard algorithm, what we wanted to do is get an algorithm which swaps three 1x3 blocks within the M slice of a 4x4 cube. And for this algorithm, we're going to come up with a different commutator to swap these three 1x3 blocks in the M slice of a 4x4. Now if we apply this commutator to the corners of this 4x4, what the result is not significant to us, but the form of this commutator, which is significant. So the commutator flows like this. We move this twice so that that corner that was down here goes into the position where the other corner was. Then we take the top and we rotate it so that this is in the opposite side of the cube. Originally the corner was on the left side, now it's on the right. Now what we're going to do is we're going to take the third corner and we're going to replace the one we just put in. And now we're going to take that third corner, we're going to put it back to where the first one originally was. And now we're going to just do a few more moves to restore the cube. We're going to apply the same idea, except for now we're going to have to apply this commutator to the inner layers of the cube and in a specific way so that we can accomplish our goal. Our goal is to find a commutator, an alternate commutator to what we originally had for the standard algorithm, which swaps three 1x3 blocks in a 4x4. I'm going to use a 4x4 supercube so that we can see what we're doing, just in case we have any questions about which center pieces are being affected here. What I'm going to first mention is, just like with that commutator I just showed you that affected the three corners, what we're going to do is first we're going to focus on a 1x3 block in the bottom. This one right here. If I imagine taking this 1x3 block and putting it up to this 1x3 block up here, it is easily done in very few moves if I just rotate these three layers twice. So moving those three layers twice, block A goes to block B. Just like the corner in the bottom here came up to this corner here with that L2 turn move. Same idea. Now what was the next portion of the commutator? After the L2 turn, then came U. That moved the corner slot, which we just put the one from the bottom in, to the right side of the cube, which is opposite side of where it originally was because it was on the left side. So we did a U-turn to move it to the opposite side of the cube, and we're going to do the same here. What we're going to do is we're going to do a U-turn, but this time instead of doing a single turn of U, since we have a 1x3 block, we're going to have to do a triple layer turn of U. That will move this to the other side of the cube. And a single layer of U is sufficient to move it to the right side of the cube. However, we're going to use triple layers because for the next move we're going to need that. You'll see. So when I do a triple layer turn, the next move in the commutator is to do R. That will take the third corner involved and place it in the slot where the first corner originally was, and we're going to eventually put it back with a few more moves. But like I said, this commutator here is not direct, as in it may seem that we're swapping the three 1x3 blocks that we're focusing on, comparing with this corner commutator, but in fact we're going to be swapping three other ones. So now, carrying out that move R, that will take this 1x3 block and place it in the 1x3 slot where the first 1x3 block was. And what we're going to do is we're going to invert that U move, just like in the commutator. Here's that move U inverted. And now the next move is to do a double turn of L again. That'll bring this block back to the bottom. Notice that the cube is mostly restored except for we have a line of pieces all around the cube which are out of place, but if we rotate the cube this way, then we can carry out the last portion of the commutator, which is U, R prime, and U prime. U, R prime, and U prime. Now if I rotate it around so we can see what we have, this 1x3 block here is affected, and this 1x3 block and this one. So it's 3 1x3 blocks affected on the cube, which is great news. This is the commutator which you just saw performed on the cube, which swapped those 3 1x3 blocks. I can convert the two double triple layer turns of L to R2X2. From there, I can convert the triple layer turns of the upper face to a single turn of the down face with a YQ rotation. I then can apply these YQ rotations to the slice in between them, the R, which will become a B. And also the same here, this Y and Y prime, when I apply it to this slice move, it'll become F prime, and those two moves, these two cube rotations of Y cancel with each other, and these two cancel with each other. That's why you apply to the moves for the cancel. Then I apply the X2 cube rotations to the moves in between them to get this. Finally, if I rotate this on a cube, the inner slice turns will be R now instead of F, which is always good. Lastly, if I invert the individual U turns, then we have another commutator which swaps 3 1x3 blocks. And I'm going to use this particular commutator instead of the one that I've been deriving to derive this algorithm, only because once we're done with this pure edge flip algorithm, if we want to convert all slice turns to wide, if we use this commutator here, it will scramble the cube, it turns out. However, this one won't. This version of this commutator won't if I just invert the individual U-turns. So that's a little unobvious because both are legitimate 3 1x3 block swappers, but that's how it turns out. So I'm going to be using this one instead, but you see how I derived this one, so yeah. So now what we're going to do is we're going to apply this commutator to a 4x4 supercube to get this result. This 1x3 block here, this one, and this one. Those are the three that are swapped. But the problem is, as I mentioned before, they all need to be in M. How in the world do we get them in M without adding any moves to this commutator? I call it shifting. What I mean is rotating moves in an algorithm so that they're at the end. So if I take this B2 in this commutator we're using, and I move it here, so that this is the first move and this becomes the last move, we don't change the number of moves that we have, and we also will get an interesting result. Still, the same amount of pieces are swapped, except for in a different fashion. If I shift the next move, U prime, then we still don't have what we want, but we'll just see what we can do. Let's just keep on shifting this and see if anything good will come out of it. So I'm going to shift R. Wow, we're getting close. So this is what we have so far. Now I'm going to shift the move U. Just move U to the end. And wow, look. Look at what we have here. We have 1x3 block here, 1x3 block here, and one right there. So they're all in M, and that's exactly what we need in order to make a parity algorithm.